So hello everyone, and thank you for the introduction. So yeah, I'll be talking about formal verification and about Morpho, and I think that formal verification will become more and more important as time goes by in the DeFi space. And I'd say the same thing for Morpho, so I thought it would be a great opportunity to talk about both. So I won't assume any knowledge about formal verification, but my promise is this. By the end of this talk, you will know what formal verification is, or at least you will have a sense and an intuition of what it is. And you would have seen examples of formal verification being applied to DeFi and being applied to Morpho. All right, so first, what's Morpho? So Morpho is a peer-to-peer layer over lending pools. So we call that Morpho optimizers. And so you have one instance of a Morpho optimizer for each lending pool, so one for compound v2, one for Aave v2, one for Aave v3. And what Morpho optimizer accomplishes is that you have the same risk parameters as the underlying pool. You have the same liquidity, but you have improved rates. So how can it do that? Well, in a lending pool setting, you have this pool supply APY and this pool borrow APY. And the fact is that the pool supply APY is lower than the pool borrow APY. And the reason for that, the main reason for that is that you have less borrowers than you have suppliers, so all the interest generated by the borrowers, they are split among the suppliers. And that's the main reason for the spread. But in Morpho, you have a peer-to-peer layer, which means that for the match amount, you have the same amount on both sides. And so you can decide the rates. And you could, and what Morpho optimizers do is that they put the rate in the middle, which means that it's a win for the borrowers because they pay less interest, and it's a win for the suppliers because they earn more. All right, and then you need to have a fallback in case one of the party exits, and you also need to have a fallback that is in constant gas, and that's not so easy to do, so that's the delta mechanism. So we have plenty of documentation. We have a yellow paper that is available also. And more broadly, if you're interested about any of the stuff that I'll describe in this talk, you can find it online. Everything is open source. And there's one last thing I didn't talk about for Morpho optimizers is that it's a layer on top, but it means that you have additional contracts. And so it necessarily means that you have additional risks, smart contract risks. And this is why you have an emphasis on security, where there are many tests, invariants. We have monitoring of different kinds on different platforms. We have audits with carefully chosen auditors, an internal review process, and also formal verification, which is the topic of this talk, and I'll explain briefly what it is now. So what's formal verification? So it's a domain that is in between mathematics and computer science. Just for that, I find it extremely cool. But also, you have a powerful idea underneath it, which is that you try to match the code with the specification, and you want to do that in a formal and rigorous way, a mathematical way to ensure great guarantees about your code. And this can be done with giving and getting a formal specification. So that's not typically what you get. So if you look at some documentation, you get more informal specification, something like returns a valid value, which may not be that useful because what's valid in that case, or sometimes you don't even get specification. So for example, if you have a deposit function, maybe the documentation is, okay, this is the function to deposit the funds, but it doesn't tell the whole story because the whole story is like what happened to the funds, what's the yield, how can you withdraw them, what's the risk associated, so a bunch of things that are not specified. And what you want for formal specification is kind of the opposite of that. You want to specify everything, and you want to do that in a rigorous way. So an example of a formal specification, simple that I wrote here, is that for every input x, if you apply f to x, you get a value that is greater than 10. So that's formal, that's great. So once you have that, what you can do is match the code with this formal specification, and out of that you get what is called a verification condition. So this is simply a formula that when you verify it, you know that the code matches your specification. When that happens, we say that the code is correct. So you cannot really say that the code is correct without a specification. You always have a specification in mind when you say the code is correct. All right, so it's a bit abstract, so I'll try to take an example. So let's take back the formula specification that we had on the bottom left. And we have this snippet of code that looks like some Solidity code. I removed some keywords to make it fit on the screen, and I'll do that for Solidity code. And we want to get a verification condition out of that. So here, just quickly, you have an array of size 3 that is holding integers. You have a function g that is unspecified. And if you want the function f to respect the specification, what you look at is that the return value g should be greater than 10, right? But this should only be needed when x is greater than 2. So this is the first line. And also in the other cases, you want v to be greater than 10. But since x is an unsigned integer, it can only happen for x equals 0 or x equals 1. And this is why you get this verification condition. So it sounds pretty easy, right? But actually, for programs that get a little bit more complex, it can be tricky. And I leave you with a little brain teaser. So let's say in the condition now, instead of x, we have x plus plus, or maybe plus plus x. So maybe we would be a little less confident about what the verification condition would be. And in the general case, it's actually can get quite complex. But what's good about that is that since both the codes and the formula verification are formal objects, you can actually apply algorithm to them, and you can do that automatically using a verification tool. And so that's one part that is done for you. So if we recap a little bit, assuming that you have your code, you have 3 steps to formally verify a program. So first, you need to come up with a formal specification. So that's the first step. Then you need to apply a formal verification tool. So that's the step we've just seen right there. And then the third step is to actually verify the condition. And verifying the condition, even if the second step is done automatically for you, verifying the condition is not always easily done like this. Like automatically finding a proof is hard. So I've seen verification conditions of 2,000 lines of code. It happens. So it's not easy to do by hand. All right, so it can get quite complex. So why bother with formal verification? And I think there are 3 reasons for that. In the case of DeFi, first is that you have small programs. So this is kind of embedded in the system. You have a limit on the contract size on Ethereum. And also, related to that, you have this open source culture with having readable code. And so it helps for maintaining the code, but it also helps to reason about the code. And this is typically what you do when you do some formal verification. So that's the first point why formal verification is a perfect fit for DeFi. And the second point is that you have a critical system where potentially you're managing a lot of funds. And you really want to get it right the first time, and that's why formal verification shines in this setting. And finally, maybe a bit less talked about, but in the blockchain setting, you have this idea that you don't want to be able to rewrite history. But at the same time, it means that the mistakes that you make, they are potentially permanent. And so, same thing, you really want to get it right the first time because this mistake won't disappear. And so formal verification gives you great guarantees here. All right, so this is the general overview of Morpho, of formal verification. And I'll give more concrete examples of how it is applied to the Morpho protocol using the 3 tools that we use at Morpho, namely Certora, Halmos, and Y3. And I'll start with Certora. So Certora is a great tool for many use cases. And in the case of Morpho, we use it in particular for data structures, verifying data structures, verifying optimization. So let's say you have one function, and then you have an optimized version of that function. Then you want to verify that they do the same thing. So you also use it for verifying the Morpho token. And I won't get into the code, but just know that in the Morpho token, you want to have an authorization setting where you give users some roles, and that's useful if you want to make the token transferable at the right time. So you have these 2 functions. The user have role, which is a view function, and then you have this set user role function. All right, just know that. And in Certora, what you do to be able to specify is that your contract is you write a rule. And a rule is just basically a formal specification where if I dissect that rule, I have this, first this Boolean, does user have a role, then I call any function f on any argument, and then I store this Boolean again. And what I say at the end of the rule is that if the fact that the user has a role has changed, well, it means that the set user role function, it's the set user role function that was called. So in a sense, what this rule means is that only the set user role function is able to change if a user has a role. And so this is maybe not the first rule that you would have come up with, so I wanted to show it that formula specification is not easy sometimes. And this is actually a really useful rule. So you can put that in your CI, and when later you add a new function, it will check for you with perfect certainty that you did not add a new function that was modifying the roles. All right, so second tool I want to present to you is Y3 that we use at Morpho Labs. And this tool is a general purpose verification tool, which means that it's not designed for Solidity directly, so you need to have this translation, and it's a deductive verification tool where it does not make any compromise in terms of soundness, and you can verify contracts with arbitrary number of iterations in the loops, for example. So it works in a modular way, and this modular way mimics very well the contracts, where when you call from the outside, you cannot change the storage variables. And so we use that to translate our code into Y3 code. All right, so this is kind of the architecture of the verification. And I want to show an example of how of a theorem that we managed to prove using Y3. So I won't focus too much on the syntax because it's another language. But basically, this theorem is really not so easy to come up with and also to prove on paper. And when you want to formally verify it, you also get arithmetic and rounding errors that you need to deal with. But basically what this is that Morpho is a contract that aggregates users. And as such, it has a position on the pool, on the underlying pool. And that means that you need to make sure that it's not being liquidated. And this is what this theorem is about. So if you take the supply on pool that the Morpho contract has, you multiply it by the liquidation threshold. This gives you the borrowing power, and you show that it's greater than the actual borrower. All right. So last example is about Halmos. And yeah, you can see that you have one really cool property of Halmos is that it's really tightly integrated with Forge. And this looks really much like a Forge fuzzing test, and actually it is, so it works if you try to run Forge on it. But when you run Halmos on it, you get additional guarantees, so pretty nice. So this particular example is taken from the data structure that is used in Morpho AVV3. And this data structures works with buckets, with ranges where the bounds of the range are powers of 2, consecutive powers of 2. And the bucket is identified by its lower bound. All right, so this data structure is improving fairness, is very efficient, and we want to also formally verify it. And this is what we do here. So we say, okay, so the bound is indeed a power of 2, and any value that we get is in the bounds, and this is automatically verified, which is very cool. So let me finish with the contributions. So I've shown formal verification that is done on Morpho protocol. So for that, we use direct verification of Solidity code using tools like Certora and Halmos. And we also defined a methodology to translate Solidity code into Y3 code and to verify it. And that's it. I think that's all there is about formal verification. But if you have more questions, I think we have a bit of time, right?
Yeah, thank you, Quentin. And we have 2 minutes for questions. And I already see one. Yeah.
Thanks for the great presentation. I am very interested that how long does it take to verify a protocol like Morpho? So if we compare the in-house effort that you've done and say formal verification services by somebody else, so how does D compare? So why did you opt in for in-house verification, basically? That's my question.
Yeah, that's a great question. So that's kind of my core knowledge. So I'm a formal verifier at heart, so I didn't opt in for that. But why Morpho did is because you need to have deep knowledge about the protocol to be able to really understand and formally reason about it. So it's not necessarily the case for every protocol, so sometimes it's a bit easier to verify. But Morpho optimizers are really deep and entangled protocols, so you need to have deep knowledge of that. And so for your question about how much time it takes, it's also a tricky question because it depends on like how much you know the protocol and like what tools you have, and also how deep you are willing to go. And if you want to really verify everything and take everything in, so that can take years, basically, so it's really almost impossible, I think, to do. But if you want to really verify the logic, which is what we did using Y3, for example, you can do that, and you can do that rapidly. So if you really focus on the important stuff, the core protocol, core logic.
Hi, I have some experience with formal verification. And the way when we get stuck, that maybe you can help us, how you verify complex interactions. For example, Morpho interacts with Aave. Aave is a huge protocol. Morpho is a huge protocol. If you start to mock a lot of stuff and dependencies, it means that your formal verification relies more on your mocks than real code, than not real code base. I think you can understand the problem. So what's your findings here? How to make this complex formal verification for interconnected contracts and a huge code base?
That's a great question. So indeed, it's very complicated. And different tools provide different ways of handling it. So in Certora, you can have a dispatcher, for example. So you say, OK, when I'm dealing with tokens, I'm dealing with this set of contracts. And this is a way that you can like have your dependency. So it's a really neat way because you can like really specify what you want. But in the general case, it can be, yeah, indeed quite complex. And so one general idea that is that I found really useful is to start small. So you start with a small dependency version, that so a mock contract of Aave, and try to come up with a formal verification about that. And then, so you have this behavior that you're mimicking. And then once you have that, you can separate it because now you only work on Aave to show that Aave actually does show this behavior. So you kind of separate the two, the dependency with a particular specification, and then you take the specification and try to verify that it works on Aave. Does that make sense? Yeah.
Okay, thank you, Quentin. And